Hello everyone, my name is Dr. Hemlata, and in this video we will see how to obtain the estimates of sampling for proportions in R. So for this, as you can see, I have written all the codes here, but I'll explain each code one by one. So before going to the analysis, we will install this package sampling book. Okay. So to install this package, I'll go to the tools and then install .packages. So here I'll write the sampling book and then I'll install. So as I have already installed it, so I'm not going to install it again, but before starting the analysis, I will load this package by library function. So here I have written library and the package name. So I'll load the library and load this package by library function. Now let us take an examples to work with the data. So here I have taken the empty cars data set, and it is the inbuilt data set in R. So let us have an idea about the empty cars data set. So to go to the help of the empty cars, to see the details of empty cars, I have written question mark and empty cars, and then I'll run it. So as you can see in the right hand side, it will take us to the help, and in the help you can see the detailed description about this data set. Okay. So let's say as we are going to work with the sampling for proportion, so we are interested in the proportion. So let us take because there are 11 variables in this data set, so let us take this variable. So I'm interested, just for an example, I'm interested in the proportion of cars which are of straight type, which are having the straight type engine. So Vs is the column which is taking two values, 0 and 1. 0 means one V-shaped engine and 1 means straight type engine of the car. So let us assume that we are interested in knowing the proportion of cars with straight type engine. Okay, so what we'll do first we will see what is the population size. So let us assume this total data set is our population. So let's see what is the length of this data set. So I'll write n is equal to length empty cars mpg. So I can pick any of the continuous variable so that it could count all the values in that. So I'm just counting the length of this variable by mpg. Okay. So I'll run this, and the number of values, the number of units in this dataset will save in capital N. So let's see what is this. It is 32. Okay, so 32 is my population size. Now I'm going to use this set.seed function with this seed number 1, 2, 3. So set.seed function is used to fix the random sample, because the sample is random. Every time we will run this sample function, we will get different units, different values in the sample. So to fix the sample, to work with the sample every time with the same sample, we fix the sample, and for this we give some seed number, and for this particular number that particular sample is fixed. Okay, so I'll fix it. Now we'll draw a sample. We can use any procedure with replacement or without replacement. So for example, here I have written the codes for with replacement and without replacement both, but for the time being I'm just taking the simple random sampling with replacement. And to collect the data, I'm using this indexing here, this square bracket, indexing bracket. So what it will do, it will collect the specific, means it will collect the rows from the population. Rows means what? Row wise it will collect the data, and because as there are 11 columns, so in the sample it will collect all the variable informations in that. Okay, so I'll write empty cars and then square bracket, and under this I'll write sample because I'm going to draw a random sample. So first I'll give the population. So I will choose the rows from 1 to, how many rows are there? N row empty cars. So whatever rows are there, I'll write 1 colon n rows. So it will take from 1 to 32 rows, because there are 32 rows. We have already seen the length of data set is 32. So it will pick the sample, it will choose the rows from 1 to 32 rows. How many rows it will choose? 10, because I have given here 10 should be the sample size. So 10 rows it will choose with all the column informations. And here I have written replace is equal to true. Replace is equal to true means what? The unit which has already been chosen in the sample may occur again. Okay, then space. Here space means what? It is also going to take the information from all the variables. So if I run this, you can see what type of output we'll see. So here it has taken the sample of 10 rows with all the column information, with all the variables, right? Now, so after collecting the sample, let's say I am interested in to see the estimate of proportion of cars which are of V shape, sorry, the straight type engine. Okay, so for this, what will I do? I will see how many cars are there which are having straight type engine in the sample. So I'm just putting this value in this argument vs1. Vs1 is equal to sum, and then it is going to count the cars which are having the straight type engine. So I'll run this and let's see how many cars are there. So as you can see, there are 5 cars with V-shape engine. V-shape, 5 cars with straight type engine. Okay, so after this, as we are going to estimate for sampling for proportions, so we will use this sprop function here, and this function works under this sampling book package. That's why we install this package in the starting, right? So let us have an idea what are the arguments it needs. So we'll just go to the help of this sampling for proportion sprop function. As you can see here in the curly bracket, it is given. That means what? This sprop function requires this package. Okay, so before working with this function, we need to install this package. Now let us see the arguments of this function. So sprop y is the first argument, m, n, capital N, level. So let us see one by one. Y is the vector of sample data containing values 0 and 1. So it is that vector in which we are interested, from which we are going to take the proportion. So here we are interested in Vs. Okay, so I'll write y is equal to SRSWR, because we will work with the sample, and then we will give estimate for the population. So SRSWR $Vs. So it will pick this Vs column from the complete data frame, and the next argument is m. It is an optional non-negative integer for number of positive events. Number of positive events means what? The event in which we are interested. So here we are interested in 1. So, and we have already counted how many ones are there in Vs. So this is just the number, and we have saved it Vs1. So we will write m is equal to Vs1. Now in the next argument, it is asking about the sample size. Okay, so n is an optional positive integer for sample size. By default, it takes n is equal to length of y. So if we are not writing this n is equal to this one, so by default it will take whatever count of ones are there, right? So though I am writing it like this, n is equal to length of SRS Vs. So again it is counting the length. So if we do not write this this here, this counts. By default it takes the length of y. Okay, and this is the same thing. Either you write or not write, it is the optional. Okay, Now the next argument is population size, that is capital N, and we know the population size is 32, so we are writing is 32. If we do not know the population size, then we can leave it this argument also. So by default it takes the population is large, that means N is equal to infinity. So if we know this the population size, we can write, otherwise we can leave it as it is and it will assume that population is large. Okay, now this is the level means what? Confidence level. So at what confidence level we want to estimate the proportion. So here we are writing level is 0.95. So that means what? We want to find out the confidence interval at 95% level of significance. Right, we can also change this 0.99. So if we write 0.99, we'll get the confidence interval at 99% level of significance. Okay, so let us run this. So we get this much of output. Let us see what is in this output. So as you can see, it is taking the finite population correction. That means it is assuming that population is given and the sample is not too large. So if the population is too large and sample is also too large, then finite population correction can be ignored and it tends to 1. Okay, but here sample is small and population is known, that is 32. So it is taking this also in calculating the in estimating the proportion. Now if we look at the estimated value of proportion, it is 0.5. That means what? Almost the 50% of the cars are having straight type engine in the population. Okay, and this is the respective standard error for the proportion, and it is calculated by including the finite population correction in the formula. Okay, and by using these the estimated proportion and the standard error of this proportion, we can also calculate the confidence intervals. So here we can see there are two confidence intervals are given, but we will look at this first one, 95% approximate hypergeometric confidence interval. As you can see, if we go to the help of this what does it mean? It means if your population is known and it is large enough, then for the given confidence level, here it is the 0.05. So at 95% confidence interval, this is the confidence interval which is calculated by assuming that the population is normally distributed, approximately normally distributed. Okay, so if we assume that population is approximately normally distributed, then we will see this first one, confidence interval. Okay, so this is the confidence interval for the proportion, population proportion, and this is the confidence interval for population total. So by this we can see in the total population, the minimum number of cars can be 8 with straight type engine, and the maximum cars can be 24 with a straight engine. Okay, so this is the range. In this range, the cars may vary from sample to sample with straight type engine. Okay, and this second confidence interval is the exact hypergeometric confidence interval, and this is this can be seen if the population is not the normal population and it is typically the exact hypergeometric distribution. So here in that case we will see this one. Okay, but our assumption is data is approximately normally distributed, then we will see approximate hypergeometric confidence interval, right? So this is how we can interpret the results. So I hope this video is helpful to you. If you found my video helpful, please like and subscribe my channel. Thank you.